Hi, I'm Dmitry Otryakhin, and I'm going to tell you about fast automatic deforestation detection. This is a recent work done jointly with Jesper Muren, Vilhelm, Niklasson, and Maxim Romashin. First, we consider a practical example of deforestation detection. On the left-hand side, there is an image of some terrain apparently suffering from deforestation. And on the right-hand side, there is a result of detection produced by one of our methods. It's a black and white image where white corresponds to forest and black is used for everything which is not forest. We use high altitude images, and this includes satellite, plane, or drone pictures. We present two models, a non-parametric one and a parametric model, which is built on top of the first. They both perform 0-1 classification, so forest and non-forest. Before this work, there had existed other classification methods, but they were built mostly on either artificial intelligence or machine learning. That's why they were computationally intense. What we aimed for was to create something which would be fast and interpretable. That's why we used the frequency statistic. And now let's turn our attention to the non-parametric model. Consider an RGB image of forest. It consists of three matrices, red, green, and blue. So we take each of the matrices and turn them into vectors and then stack these vectors together to obtain a new matrix X here. We do it in such a way that that preserves triplets of red, green, and blue pixels, although now we have completely lost all the information about pixel locations. Then we obtain X bar, which is mean vector, three-dimensional mean vector, and the 3x3 covariance matrix. Now suppose we have two images, a reference forest image and an arbitrary test image. We obtain x1 and x2, and then we compute the Mahalanobis distance between these two images according to Formula 1. X bars here are just sample mean vectors, and this sigma hat is the pooled covariance matrix which is given by Formula 2. So sigma hat actually describes dependencies between colors. Since RGB images were used, then all the numbers in these matrices here are from 0 to 1. And that's why we know that moments exist. So there is no problem with formulas 1 and 2. Now we switch to the following theorem, which is the key result for this whole work. It says that assume that we have x1 and x2 ID samples with potentially different numbers of rows n1 and n2. If x1 and x2 come from the same p-varied distribution with a finite mean and finite covariances, then with the n1 and n2 going to infinity, the rescaled Mahalanobis distance converges in distribution to high-squared random variable. This expression on the left-hand side is actually the two-sample t-square statistic. And this result is used as a base of multiple hypothesis testing framework. So what we do, we take a set of forest images and a test image. We compute all the Mahalanobis distances for pairs, test, and the reference image. Then we extract the minimal one, and then we see if this value passes a certain threshold or not. If it passes, then it's forest. If it does not, it's higher than the threshold, then we tag it as non-forest. This threshold is obtained preliminary during the training procedure. This approach is fast because the only thing we need to compute is d square, and this one contains only mean vectors and 3 by 3 covariance matrix. Since we described all the distributions by mu's and sigmas, then we captured the dependencies between the colors, although we have completely lost all the information about how color intensities are distributed, so we don't know anything about distributions inside each channel. And this is something what the parametric model was built to cure. But before going into details, let's take a look at the data. So this is again a picture of forest, and we plot empirical density functions for each channel. So this is red, this is green, and this is blue. Empirical density functions are shown as black. We also plot here stable, gamma, and normal distributions fit to this empirical data, and we see that stable distribution shows almost perfect fit. And we tried also many other distributions, not only normal and gamma, and we realized that only stable distribution is as good as this. We attribute it to the fact that stable distribution actually has a lot of flexibility with its 4 parameters controlling the shape. And let me remind you what this type of distribution is. So stable distribution is the one whose corresponding characteristic function has the following form. Alpha parameter controls the decay of the tails. Beta is an analog of skewness. Sigma here is a scale parameter, and delta is the location. There is no explicit form for the density function, so we have to work on the characteristic functions instead. And now we return to data extraction procedure. Suppose we already have obtained this X matrix. Now what we do, we compute for each channel, we compute the parameters according to the Kutravelis regression type estimation procedure. We use these parameters to obtain the theoretical characteristic function for each channel, and also we compute the empirical characteristic function as shown here. We need to impose 2 restrictions now. So first of all, test samples are much smaller than the reference ones. That's because Kutravelis technique is still quite computationally demanding. So we don't want to do it during classification, we want to do it only once during the training procedure. The second restriction is that the distributions in different channels are independent. So we have lost all the dependencies because we used the one-dimensional stable law. This could be fixed by using the multidimensional stable distributions, although we haven't done that yet. And now we define a new vector Wn in the following way. And we present a proposition saying that for any stable random variable x, it holds that the rescaled Wn converges in distribution to a normal random variable. This sigma is defined through its elements as shown here. So it depends only on the characteristic function. We design a new Mahalanobis distance and a new Hotelling t-square statistic as shown here on the left-hand side. So this is our new t-square statistic. Using the previous proposition in theorem 1, we can show that this one converges in distribution to a high square distributed random variable. This result is used in a similar way to what we saw in the non-parametric case. There are 2 advantages and disadvantages. So first of all, the advantages are that we now consider distributions in the channel. And also classification is also fast, because there is not much to compute. So sigma here is pre-computed and Wn contains only characteristic functions. The drawbacks are that this method is slower in training because we used Kutravelli's parameter estimation. And another thing is that we have lost dependencies between channels. To conclude, I would like to mention that there are many practical applications to these methods, and also we can extend them to multi-type classifications as we used multiple hypothesis testing procedure. Another thing is that the non-parametric model performs a bit better on small data sets, as was shown in numerical studies. We haven't taken a look at large data sets yet. And the last thing to point out is that there are two packages being prepared for submission, R package and the Python package, with the techniques that I have discussed. So I hope they will come out soon, and thank you for your attention.